say, about development of efficient QMMM scheme using graphical video cards, and also a new development of time-dependent DFT in QMM schemes that allow us to make some interesting things like electron dynamics and things like that. Okay, I think I can go fast here because I think everybody do, almost everybody do QMMM in this meeting, and later Dario and others will talk about this a lot. So you know about QMM, the system in which one part is QM and rest is MM. I think today we are talking a lot about it. Okay, I work with Leo. Leo is a software developed in our group. The original version was wrote by Dario in Fortran 77 in 1992, and we work with this code last 20 years, maybe more, and now with the collaboration with people with computational science, we convert to Fortran 19C and CUDA to use video card. And it's called Leo because it's fast and accurate. But here, if you want to download or use it, it's in GitHub. And this afternoon we are going to do some work and use Leo and Leo with Sander to make some things similar that I present here. Okay, the quantum model on Leo is based on density functional theory. I think most of you know about this. In this theory, the density have a fundamental role, like work function in other quantum approach, and we can write the energy as a functional of density with different terms. You have a criterion of good density when the energy associated with the real density is always lower than the energy with another density. But in this scheme, this term have all the magic, and in this term have the quality of the results and the computational cost. So we work a lot to this term better. DFT has a great cost accuracy relation, so it's a choice to use in bigger system or for molecular dynamics in which we have to make this computation several times. So this is, for example, this is a system I work. It's similar to some that I see yesterday. This is a soluble domain of a protein, copper transport protein, that has a self-phosphorylation step, and this is the QM system on this for study this reaction. I take this like a study case for see the cost in computation before optimization and use of GPU, in which the exchange correlation term use the most demanding part, but any of these portion of the calculation are ported to GPU at the present time. Before that, we take 76 seconds per step of molecular dynamics. This makes the system impossible to trade with DFT. That's why many of you use DFTB or something more cheap, because if I want make a free energy profile with umbrella sampling or Sharsinski or whatever, take a lot of time. So we use this to make the thing faster. GPU, I think maybe this slide is redundant because I think almost of you already know about the power of this kind of car. Has a lot of pros because have a massive computer power, they are programmable and have an excellent cost power rate. But have a lot of cons, like you have to produce a code especially for this device, thinking about the different kinds of memory and the use, and with trial and error since how to use this hardware. So to do this, we need the help of computational scientists who knows more about it. So okay, this should be staged, I think. This is all the stuff. This portion was with a lot of work because everything of these slides of that pie have a different problematics, so a different solution. But with a lot of work with this system, we passed from 76 seconds per step to 3.3 seconds per step. So now really we can, this is all the time for any stage, and we can reduce the time, the execution time per step to 3.3 seconds. Okay, just a comment. The program, the last work on this program, we use hybrid computation, in which we use both GPU and CPU at the same time, several cores and several GPU. And this, if you do that with an smart way, you can obtain a superscalar behavior. I mean, this the blue is the theoretical improvement for use more cores, but in red is what we obtain. This is some complicated. If you want to know more about this, we can talk later. But just for say that you can do things interesting like that. This is why, but I have to talk much about the code and how to work. So I will pass because I want to talk to you about something more exciting. I think for all of you is expanding the capabilities of UMMM simulation in a different way. This is allowing to simulate things that we are not familiar with. This is using real-time time-dependent density functional theory. That we can do with this is electron dynamics. See how the electron moves, not nucleus. This is interesting with when you study interaction with light, like absorption, emission, or things like that. Electron transfer, this is the most important for me now, how the electron go from one part of the system to another, biosystem or whatever. Non-Bohr-Oppenheimer dynamics, there are some cases in what we use Bohr-Oppenheimer, the Bohr-Oppenheimer dynamics, in which the dynamics of the electrons and the nucleus are separated. In some cases it's not true. Photochemistry, like I put energy with light and things happen, etc. The theoretical background is like identical like DFT, but other names. But you have the time-dependent Schrödinger equation. You have still Combe-Sham theorem. You have Runge-Gross theorem, but it's equal. It shows that the density, but now as a function of position and time, the density depends on time, is univocally binded with a potential also depending on time and the work function. So the density as a function of position and time has the same entity like the work function. And better, we have an equation who tell us how the density evolves in times. We just need to computate the commutator between the Hamiltonian and the density. You see this, I can compute this like static or non-time dependent DFT. So we have all the ingredients, so we just have to put together. And then we have to integrate this equation, and we can use some propagators. This is one more simple. It's like a Berlet, but for the electrons. And there is another. Doesn't care a lot. This propagator allow us to get a bigger time step. The time step here is 2 orders of magnitudes lower than the time step that we use for molecular dynamics. So the first question about this is work. It's a honest question. What we can do is obtain the absorption spectra of a molecule by the Fourier transforms of the dipolar moment. Okay, we perturb the system. We give a kick with a delta of electric field, and we see how the dipolar moment is evolved. We are going to do this in this afternoon with everybody. So here is the comparison between real-time time-dependent DFT and linear response. Linear response time-dependent DFT maybe some of you are using in Gaussian when other programs use this. That is what they call time-dependent DFT, but we call linear response because it's not really a dynamic of electrons. They just has some computation with a steady state. And the real time basically is work. But better than compare with linear response time-dependent DFT is compared with experimental. And effectively, the frequency of obtaining of the transition obtained are in very good agreement with linear response and experimental when it's available. This is in gas phase, so some molecule we don't have that in gas phase. This is, remember, this is an ab initio model, so I don't put anything about the molecules on it, anything, and we reproduce very well the experimental value. So I think it's work. And better, it's interesting working with this because it's a new area, because it's very expensive to compute this. So it's an area which is in construction. So this is the first program who can do real-time time-dependent DFT in QMM scheme. So we can see, for example, the solvatochremic effect in forma mida. We are going to do that in the afternoon. exactly this. And we can see if we compare the spectrum in vacuum and in aqueous solution, a shift of the absorption spectra that is in really good agreement with the experimental shift. So works time-dependent DFT and works the QMM. And also if we use a protein, because LEO works together with Amber, with Sander in particular, and we compute any molecular that you can use in Amber. So we can use a heme group in a heme protein, and we can see that this work. And better of that, this is a carotene molecule, and better of all, we can do very nice movies. Like this. This is the changes on the density when we excite with a laser on the right frequency. It's very dark. It's just a little dark, but you see the blue is when the density is deployed or diminished, and red is increased. So you can see that here the polar moment oscillates with the frequency associated with this transition, and very nice. But for make spectrum, there are linear response works well. So we can use this strategy when we have a linear response that we can use. But there are something that the linear response can't do. That is why we develop this, or we use these techniques, is to study things like electron transport. Electron transport, really, there are some other forms to study this phenomenon, but this is the more natural way. Seeing like the electrons moves from a place to another. So we start studying the electron transport, because all the techniques are in development. We have to create tools, to create frameworks to make this, because it's all new. So it's interesting. A simple model for electron transfer, we can take alkene and define a source, a bridge or molecule, and a drying zone. So if we polarize this, we have more electron or more density in this place, we can see how these electrons go to another place. So we can know about the conductivity of the system. We can study that from static wave function. There are some development in this, but have some problem like coherence and things. In some systems this don't work very well. I don't have time to enter in details. Another this work well for many systems, but not for all. One option that are in like Taylor theory is polarize with an electric field and release the electric field and see how the electron move, but we don't have a really steady state in which condition we should be measure the conductivity. But we develop a framework to study this from a steady state. But this is complicated because for how a steady state you have to the electron move from one side to another, and you have to, with some mechanisms, put the electron back to this. Okay, so not electron, better some density. How we do that is putting a term in, in, the, in the evolution of the density, because depend when reference density. This reference density, this is like umbrella sampling for electron. Okay, we have a reference density. The density in DFT, I don't know if anyone knows. This is a matrix. We have elements with mixing any part of the molecule. So these elements, these reference density elements are fixed to 1 when the molecule was polarized with electric field. If the element belongs to source or drain part of the molecule and is equal to the density if not. If belong to the molecule or bridge molecule. Okay, so with this term, the molecule, the density moves, but this go against this movement. Okay, but we want a plot of current versus potential, so we can have the conductivity. The problem is that the current depends on this parameter, and the potential is not clear because we polarize with a potential, but when we remove the potential and use this term, the effective potential that the molecule is equivalent is not well defined. So how can we remove this problem? Is calibrate with the potential with the Millikan charge. If we plot the charge bias, this is the difference of the charge between source and drain as a function of the potential applied. If we do many experiments in which we put electric field, this is all made without electrodynamics. So we have the wave function where when the potential applied is like this value, and we see how the Millikan charge are in source and drain. So we have a calibration curve, so we can see the Millikan charge in any time of dynamics and relate this with potential. Okay, if we do that, this is all the curves with different parameters. Okay, this is the gamma parameter. But if we use the calibrated, we have independent from the parameter result. So we are very happy. This is the first approach of this. What more? Hello? Okay. Okay. And here we have this is very amazing. We have learned something very amazing that, for example, that the alkene are more conductive than alkane. Lo practiqué, pero no. You know, alcano y alkeno no me sale. Perdón. This is this one, the green. Conjugated alkene. This is alkane. So we learned that the alkene are more conductive than alkene, but this is obvious. Just to try that the thing works. Even more when we have a bridge bigger, the conductivity is slow. It's slow, no. Less. And this was in comparison with the black one are the computed with a different method that is static and is a validated method. We have almost the same curve. So we are happy that this also works. This is is a work that is very fresh. Is now evaluated. It's not impressed, but I think very soon. So this is all. Have excellent on time. Too fast, many. The work in progress. This is pseudo potential is almost ready. Nico is working on this. We are writing the paper right now. But, remind the forces. Use this moment to make a demand for Nico. We are working also in a different way that we can do dynamics of nuclei and electron simultaneously. This is Ehrenfeld dynamics. It's called that we can do things like photochemistry or things like that. See how the energy how we put in electron goes to the nucleus. Very interesting. And we going to already start to see the process electron transfer in system more interesting, like Chosalkin or things like that in a QMMM scheme, and release the program with the appropriate documentation. I put this just for make a promise. I have to do the documentation for use the program. I never do, but someone more I want to say. Well, this is the people who works in this program. There are many theoretical chemistry chemists that work. Darío, in particular, start the program. Damián Sherlis and Uriel Morzán, Francisco Ramírez are the time-dependent team that I work with. William Agudelo works also in the development of OpenShell Leo. Well, Nico, everybody knows Nico, and Fernando Bobeta. Also, some informatics that these two are now working for Google, making a lot of money, but no fun. No fun. No, they are in Switzerland, so I think no fun. But a lot of money and chocolate. Esteban Mosco is the investigator of computational science that I work mostly, and it helped me to do Leo fast and accurate enough. So that's all. Thank you. Yeah. No, but in this kind we evolve the density, not the orbitals. There are many implementations who evolve the orbitals, and it's very similar. We discussed about implementing this because it's very simple to do in the other way. But we evolve the density. I really don't know because I never do the evolution of orbital. I think it's mostly equivalent. Nico do with other guy the evolution of the density, but the different density associated with each orbital is kind of the same, but it's not the evolution of the orbital, but the density. Instead, evolution of the global density, the density of each orbital. This is more expensive. But I think that if computational more expensive. But the evolution with the orbitals, I don't see the difference because I never did that. So I really don't know what the real advantage. Yeah, no, I don't tell. The current, because in a steady state, this density don't evolve anymore. But we have this term are not zero, are equal and compense each other. And this term we can associate with the current, because this term is how the density moves from source to drain, and this term puts the electron back from drain to source. Okay, and this we can if this term is big, it seems that the current is big, because there are many electrons that are going from one place to another. But this term put it back. So it's a stationary condition, exactly. But this the sum is zero, but each term is not zero. Has a value, and the value is related with the current. Yes. No, well, you can see like an open system, because this term remove electron from the source and put in the drain. It's continually doing that. Yes, yes, always. That is why this is zero. Instead, this term is not zero. So the molecule is polarized. You have a potential, a gradient of potential, but the density don't move because this term is getting back. Yes. It's like that. Yes. It's equivalent. Yeah, yeah, it's on GitHub, but there is no good documentation. But if you email me, I tell you how to use it. It's here. It's commented a little bit. Half in Spanish, half in English. Here, you can download here. This afternoon we are going to use a little bit. So it's very easy to use if you already use Amber. And if you look, you can make it work, because